Hello everyone, welcome back to another stream. So I just came back from my maths paper 3 and today is a very depressing day. So I believe I performed it's very very badly compared to what I'm actually capable of. So I kind of overestimated myself and I didn't study much for paper 3 and I believe that's what really made me do really badly for paper 3. So I got like a few questions where I already realized that I made a few careless mistakes after the exam, but some of it is perfectly fine. Like you have 11 questions, I think at least 5 of it I had like careless mistakes, so that's very quickly like 10 marks gone already. So that's really horrible. Uh, it is really depressing to know all of this stuff and knowing that you can't really do much about it, even though like you can do it, you understand it, but due to the time constraints, it is a bit, yeah, it does suck a bit that, yeah, it's not that you can't do it, it's just because of all of this. Yeah, but it is my fault also because I did kind of overestimate myself when I went on to take the paper. Yeah. So there's this one guy online, one Chinese guy. He she I don't know was finishes all of these papers and puts out the answers online, but only after the exam. So only after the exam, we would receive these answers. We got the answers, and then we're not sure if it's correct as well, but yeah, it's a high chance that it's correct. So yeah, the answers were like a bit different from mine. So that's how I know like there's a few questions that I really shouldn't be getting wrong, but I ended up getting wrong anyways. So it does kind of suck. So I think worst case scenario, I lose like 15 marks out of the 75, which gives me like a low, like a 79, which is horrible, like incomprehensible. Let me just run a quick calculation. So 75 minus 15 would be 60. 60 over 75. Okay, that'll still be a 80, but that's 80%. So if I do get like a 60, then all my hopes for A star would just be thrown out the window. Yeah, it does kind of suck knowing all this, but that's why you must move on, I guess. Okay, back on topic. Today we are going to be doing paper 5 of physics. So this paper is actually more like essay based. Let me just show you. It's more essay based. Like you have to write long paragraphs, like very detailed paragraphs of how you would carry out experiments, and there is very few calculations in it, but of course there are still calculations when you need to like, but it's very simple calculations. So the thing about this is you need to know like the keywords, what you must include in these paper 5 questions. So first thing is defining the problem. You must know the independent variable. For those who don't know what independent variable is, it's a variable that you are constantly changing. Like let's say the pressure in a gas, in a volume of gas. So you will constantly change the pressure to see how high it is, how high the lever is pushed up, something like that. So your pressure will be your independent variable, and the degree in which it is pushed up is your dependent variable. So dependent variable is, like the name suggests, dependent on the independent variable. So it changes based on the changes of the independent variable. So that's one thing you must state. And also, second, you must state what must remain constant. So in that case, normally you would like keep the temperature constant. Constant temperature, yeah. But I haven't seen this one. I'm just taking the mark scheme as an example. I haven't seen the question yet, but I'm just giving like an example. Okay, methods of data collection. So of course you have to draw the whole. You'll see later, but you have to draw the whole setup to show like how the final setup will look like once you're done setting everything up, and that produces marks for like this part. Although it is not here, probably around. It's not here, but yeah, this is a 2018 paper, so probably it's not included here. Probably it's a different way to do it. But yeah, mostly the questions now they'll ask you to draw. So, but most importantly, you must define the problem first. Next thing, method of data collection. How you would collect your data. Labeled diagram of workable experiment. Yeah. Okay, so this is the part you have to draw. So you would draw your sealed container, tube connected to a pump, and salt solution. Okay. And then workable method to heat salt solution with sealed container. Okay, so this one you would just draw like a Bunsen burner below it, or something like that. Description of pressure gauge or manometer to measure P. So you would have to draw. Since it says description, so you might have to draw it, but later on you would describe it. Like connect a pressure gauge into the volume of gas and to measure P, something like that. Next one, use of a thermometer to measure theta, or label thermometer in salt solution in diagram. So this one you will just draw a labeled thermometer. So you just draw a thermometer inside the salt solution, like poking into the salt solution. So that's already 1, 2, 3, 4, 5, 6 marks. So next thing, method of analysis. So method of analysis, normally for all questions, you just have to draw, say you want to plot a graph. But plotting a graph, you would have to state like which is the y-axis and which is the x-axis, and which is the gradient and which is the y-intercept. So how they know like which one's the y and which one's the x is it's actually given in a form, in a equation. They give you an equation, and you would just have to pick apart from that equation which one is the y, which is the x, the gradient, and all that stuff. Next thing, additional detail including safety considerations. Safety considerations. So of course when you're heating, you would want to like prevent yourself from getting burnt. So of course you'll wear gloves, safety gloves, and maybe a safety screen relating to pressure, density of salt solution. Okay, this one is just additional detail. This is not a safety consideration. So you'll just state that to measure the density of salt, you'll use M over V. Measuring cylinder to measure volume, and difference in top pan imbalance, scales readings to measure mass or salt solution. You use a measuring cylinder to measure your volume. So this whole part is actually just you describing how to set up the experiment, I think. Slowly, gradually decrease the temperature and pressure. Okay, just how you carry out the experiment. Measure P and theta when salt solution starts to boil. This is your equation. So this is your y and x plus c. Relationship valid if it's a straight line. Identification of when salt solution starts to boil. So you would have to say wait until you would see like how you would want to see if water boils is when there's like bubbles starting to form on the surface. So you have to say like wait until you see bubbles forming on the surface. That's when it starts to boil. Another one would be checking that density of salt solution is constant. Add water to keep density constant. Take multiple solutions from a large volume. Oh, okay. So yeah, you want the density to remain constant. So you also have to state how you're going to keep the density constant. So next one. This one, they do give you like, firstly they ask you to find the gradient, of course. They give you an equation and ask you to find the gradient. Yeah. And the rest is just, let's just do a paper first and we'll see exactly how we're going to answer it. Still kind of bummed about the exam because I know I could do like a lot better. But yeah, this is really my mistake. Like, you know it's your mistake, but you can't do anything about it. So you just end up feeling like sorry for yourself. Like, you know, you shouldn't be feeling sorry for yourself because it doesn't do anything, but you still feel sorry for yourself, you know. So it's not something easy to get rid of. Okay, let's start. So we'll start with the first one. Let me write down the syllabus code first. 970252 FM231. Well, I did stay up until 12 yesterday to do the papers, so maybe I shouldn't be doing that. Maybe that's making me not as refreshed for the exam. Okay, we gotta stop making up excuses. Okay. Yeah, first thing we have to do is draw a diagram. So we read the question first. Let me get my pencil first. Second part, so I'm just gonna use my pen. An electric pump is placed in a container of liquid. A model wind turbine is connected to the pump by a cable as shown in figure 1.1. Okay. The turbine is placed in moving air. As the turbine blades turn, electricity is generated and the pump pushes liquid through a vertical pipe. Okay. The frequency of rotation of the turbine blades is F. The height the liquid moves is H. The mass per unit time of liquid leaving the top of the pipe is Q. It is suggested that Q is related to F by relationship, so this is our formula. Q GH equals to C plus D F Q, where G is the acceleration of free fall and C and D are constants. Plan a laboratory experiment to test the relationship between Q and F. So the relationship would be of Q and F, so your Q would already be your Y, and your F would be equals to your X. Draw a diagram showing the arrangement of your equipment. So here I will straight away write down, or we can draw first. Let's draw first. Okay, so it is first thing, we just draw the exact same layout from what they gave us, the turbine, and we have the cable connecting to the pump, pushing the water up a height of H. Make sure you label everything. Okay, so first thing we need is to measure the height h that the water is being pushed up. So you would need to draw a ruler, a meter rule, because first thing we want to do is measure the height that is traveling. So we draw a ruler, and we will need to draw like a clamp holding onto the ruler to make sure that it doesn't move around. So here we have a clamp. next thing we do, we need to measure the frequency in which the blades turn. So the frequency, how we would measure it is actually, we would have to use a stopwatch, honestly. You have to do it by eye. But I think that's a better way to do it other than stopwatches. Let's say we use a light. I don't think light gates will work for this one. Okay, let's do like video recordings. So we have we'll just draw a camera. Recording the fan as it rotates, so that we can have a video playback of the blades to see the period of one blade rotation. What else? I think this one we don't really have to draw much since most of it is already drawn already. Frequency, okay, we can calculate the frequency. The height of the liquid moves, okay, that we can really measure that. The mass per unit time of the liquid leaving the top of the pipe. Okay, so we want to measure the mass in which the liquid leaves the pipe. So we will need a sort of balance below it to measure the difference in mass. Okay, we need a balance. To measure the amount of the mass of the liquid leaving per unit time, we would use leaving the liquid per unit time. I think for this one we would need to use a sort of I think the camera will cover it as well. Okay, that's what I'm going with. Okay, so that's all we need. And yeah, the camera will capture everything. Okay, so first thing we need to do, let's identify the independent variables. So for number one, we'll state that independent variable is, so Q is the mass per unit time of the liquid leaving the top of the pipe. Oh, we need something that provides the moving air as well. So let's just make so we'll draw a fan. Fan going. Okay, so our independent variable would be F, which is the frequency in which the blades rotate, and our dependent variable would be Q, in which, would be Q, the top of the pipe. Okay. Now, and then next thing we will need to do is find what is constant. So what should remain constant would be the liquid. Yeah, I'm guessing the liquid must remain constant, like the density of the liquid. So density of liquid has to remain constant. Okay, that's 2 marks. Moving on, we describe the experiment, how it's going to go. So first thing we'll do is how we will set it up. Firstly, attach. Sorry, the wind turbine is already one item, so I was thinking of assembling the wind turbine then. Attach cable from wind turbine to the pump with the pipe. That's your first step. Next step, place the pump and pipe into a, just write that as a container or a beaker. I think that's a beaker. So just a container. Into a container filled with a liquid of constant density and volume. So it shouldn't be volume, just constant density. So now we've assembled the wind turbine and the pump and pipe, and we've put it into a container of liquid. Next thing we'll do is place the container with the liquid and pump and pipe inside onto a balance, electronic balance. Let's make it very specific. Electronic balance. Then our next step, record the initial weight readings from the electronic balance. Next thing, so we've recorded the weight already. Now number 5, switch. Pen's run out of ink. It's dried up. Okay, switch on the fan and position it so that, wait, sorry, let's position the camera first. or 5. Position the camera so that the whole setup is in view. Okay, next thing, B2, 6. Switch on the fan and position it so that it directly blows towards the blades of the wind turbine. So we forgot to measure the length of the pipe actually. So we still have to state that, but you will have to state this before. So I'm gonna state it on step 7, but yeah, it's best to state it in like step-by-step procedure. So next thing, place a meter rule parallel to the pipe to measure the height of the pipe. And secure it with a clamp. Ensure that ruler is completely parallel by using a set square prop against bench and ruler. Okay, so we know what G is already, and we have a method to find Q, we have a method to find H. C is a constant, D is a constant, and we have a method to find FQ. Okay. Now we move on. Once we switch on the fan, we go on to our next one. Set the camera to record the whole experiment. And then next step, we would have to the camera is still recording. Change. So we have to put varying F now. So we will have to vary change the speed of the fan blowing at the blades. Vary F of blades by changing the speed of the fan. Okay, next step. Let experiment continue for 10 seconds before changing speed of fan. Next. We want to make it as detailed as possible. So we've already got all the method to how the experiment's going to go. And now we just gotta do the data collection. Once sufficient data is collected at least 5 different speeds, if you can see, stop recording, and then data collection. Play back the footage in slow motion to determine the frequency. We have to go with time period first. Time period of one oscillation of the blades. Next one. Now we have to find a way to measure the F, as F is equals to 1/T. Use this formula to calculate the frequency. Now we've got the frequency. Now we just have to calculate the. Yeah, I think the thing that must be constant is the height of the pipe. So let's just state that down as well. Height of pipe remain constant. Okay. Next one, we just need to calculate the Q, the mass per unit time of the liquid leaving the top of the pipe. Oh, it's just jumping off the pipe like that, so it's not being moved to somewhere else. Oh, okay. So since it is leaving the pipe, you might want to draw another connection to the pipe, and then you just bring it over to another container that's outside of the balance that's set on the ground. But honestly, if you do like this, you could put the weight balance on the second container and calculate the change in mass as more water is being added to the weight. But of course, you can also do the change in mass of the initial container of liquid. Yeah. Okay. To measure Q per unit time. Determine the change of mass of the container containing the liquid in a time of 10 seconds and divide the total mass lost by 10 to to determine the rate of mass per unit time leaving the pipe. Okay, so we got to calculate Q already. Now we just need to state the total number of Qs we need to calculate. Obtain different how do I say it? Repeat X step number 15 for different values of f. And there we go, we have all of our data, and now we just want to plot it. X17, plot a graph with, so since f is our independent variable, we would put it at the y-axis with f in the x-axis, in the x-axis, and q in the y-axis. Any safety precaution? Oh, sorry, we continue first. Start 18. If straight line relationship is supported. Okay, so we have the procedure to be followed, the measurements to be taken, the control of variables, the analysis of the data, and now we just need safety precautions to be taken. Sorry, maybe we just expand on the graph even more. We just state which one's the gradient. So based on the QGH equals to C plus DF cubed, and we try and make this into y equals mx plus c. So df cube is already our x value. So no, sorry, that's already our mx. So our x would have to be f cube. It's f cube. So first thing we do, Q, we move our GH over, so we have C over GH. These are constant. Plus D over GH F cube. So our equation is already F cube. We know that our x is F cube, so we have to change our plot graph. So we have to put plot graph with F cube in the x-axis. And then from this we can state that with the y-intercept, sorry, step, what's this, step 15. Step 15 with the, sorry, this is step 18, with the gradient being d over gh and the y-intercept being c over gh. Yeah. Okay, moving on. Now we have the whole graph. We will just state the safety precautions. It's going to make it in like one step. Safety precautions, of course you have to mind the blades of the wind turbine. So would wear safety gloves. When tampering with the blades of the wind turbine. And in case what other safety precaution would we have? So maybe the cable and liquid. So we want the non-conductive liquid to be used preventing electric shocks, and probably a non-conductive so in case the pump has like too much pressure, then the pipe might like burst. Set up screen in case pipe bursts from pressure overload. Okay, I think that's it. Okay, let's move on. This is a whole 15 marks. 2A. The student investigating standing waves in water. A sound source is placed at the bottom of the cylinder containing water. A microphone attached to a rod is placed above the sound source. The sound source is connected to a single generator. The microphone is connected to an oscilloscope. The signal generator is set to a frequency of F. The microphone is moved up away from the sound source until the maximum amplitude is observed on the oscilloscope screen. The distance d1 between the microphone and the sound source is measured. The microphone is moved up further 2 cm. The microphone is then moved down until the maximum amplitude is observed on the oscilloscope screen. A second value d2 is measured. The average value of d is calculated. The experiment is repeated for different values of f. It is suggested that f and d are related by the equation v over f is equals to 4d plus k, where v is the speed of sound in water and k is a constant. A graph is plotted of d on the y-axis against so d on the y-axis against 1 over f on the x-axis. So we have d is equals to m 1 over f plus c. So from this, we try and make our equation here to look exactly the same as what we have from the graph. So firstly, we move our f to the other side. So, oh no, we don't. We just have v over f is equals to 4 bracket d plus k. Expand it, you have v over f is equals to 4d plus 4k. And now we would move divide everything by 4, so we have 1 over 4 vf. Sorry, so it's just v over 4f is equals to d plus k. And if we move our k over, we have v over 4f minus k is equals to d. And this somewhat resembles our graph, which is d on the y-axis and half 1 over f on the x-axis. So from this, we know that 1 over f is the x, so we separate the v over 4f. We will have v over 4 times 1 over f. So therefore, our gradient is equals to v over 4. And our y-intercept is equals to negative k. That's just 1 mark. It's really simple. Okay, for b. Values of f, d1 and d2 are given in table 2.1. Okay. Calculate and record values of 1 over f times 10 power negative 3 hertz and dcm. Table 2.1. Include the absolute uncertainties of b. So d would be measured the average value. So we want the absolute uncertainty of d. So we will have to calculate. So firstly, we would just do the f. Let's do the f first. So we will have 1 over 1.5. That gives us 0.667. So we have to take the powers, the 10 to the power of 3 into account. So we have 1 over 1.5 times 10 to the power of 3. However, over here, we already have the times 10 to the power of 3, which is below here. So we already have that. So we just take the 1 without the power. So it's just 1 over 5. 1 over 1.5. And then next one, 1 over 2.1, that gives us 0.476. Just give it the 3 significant figures. And then 1 over 2.8, we have 0.357. Next one, 1 over 4.1. 0.244. Next one, 1 over 5.2. We have 0.192 and 1 over 7.6. We get 0.132. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay. And then that's our 1 over f value. But then for our d value, we actually have to do 24.9 plus 24.5 divided by 2. That gives us 24.7 plus minus, let's find the absolute uncertainty, which is 24.9 minus 24.5 divided by 2. That gives us a 0.2 absolute uncertainty. And for the next one, 17.2 plus 17.6 divided by 2. That gives us 17.4 plus minus absolute uncertainty of 0.2 as well. Moving on, 12.4 plus 30 divided by 2, 12.7. And we find the absolute uncertainty, 0.3. Moving on, 8.1 plus 8.7, we get 16.8. Sorry, forgot to divide by 2. 8.4. And then the absolute uncertainty would be 0.3. 6.2 plus 7 divided by 2. 6.6 plus minus 0.4. And then for our last one, 5 plus 4.2 divided by 2, you get 4.6 plus minus 5 minus 4.2 divided by 2, 0.4. So our answer these would be 0.2, 0.2, 0.3, 0.3, 0.4, 0.4. We'll go turn on the lights first. Now we have to plot a graph. So plotting a graph is actually, I need a graph paper, but I don't have a graph paper. So you have to include the error bars. So I'm not going to do this, but I'm going to tell you how to do it. C1. Plotting D against 1 over F. So you put your average values on the top hand corner, because it's D against 1 over F. So you'll have like, let me draw it like this. D, F. So let's say you have, you look at the mouse, let's say you have like one here, the Cartesian plane, and then you have your D on the top and your F on the bottom. So your error bars, since you have your absolute uncertainties on your D, so your error bars will have to be a vertical error bar. Yeah, just plot corresponding to the values you get, and your error bar must be in the magnitude of your absolute uncertainty. So let me write that down. D in Y, 1 over F in X, error bar, vertical, on point, points, relative in size to absolute uncertainty. Okay, and then from that you take the, and then that's your graph actually. That's it, 2 marks. That's your graph. That's your error bars. Draw the straight line of best fit. So your straight line of best fit will just have to be the point that separates all of your coordinates evenly. So you have like 3 on one side, 3 on the other side. So it has to be evenly, perfectly even. And they have to be as close to each other as possible. The points have to be as close to the line as possible. And your worst acceptable straight line, you would just try and draw your line and make it cut the error bars, like either the most shallowest part, meaning all of your error bars, the lower end of your error bars, or the steepest part, the highest end of your error bar. Okay, determine the gradient of the line of best fit. Include the absolute uncertainty in your answer. So gradient, normally for AS, they'll ask you to draw a gradient triangle. So I would suggest for this one, E2, you draw a gradient triangle as well. So a gradient triangle must be at least half of your whole best fit line graph. Okay. Half of your best fit line graph. You take the 2 values. Do not take the values in your graph here, because then you are not using you're not determining the gradient of your best fit. So take the values of your best fit line from the triangle. And yeah, from that you can calculate your gradient, y1 minus y2 over x1 minus x2. Determine the y-intercept of the line of best fit. So from that you can already see that, let's say your line intercepts here, so y-intercept here, your best fit, just see where your best fit intercepts. So you have to include the absolute uncertainty in your answer as well. So maybe your absolute uncertainty just has to be in the range of 0.2, 0.3, and 0.4. It just has to be in that range. Using your answers to A, C3, and C4, determine the values of V and K. Include appropriate units and include the absolute uncertainties in your answer. So the value of A, C3, gradient, your gradient here as well, and your y-intercept. So from that, you can actually use that to calculate your gradient. So we calculated just now, our gradient is v over 4. So from that, we can already do v over 4 is equals to our gradient, and that gives us our v. But for our k, k as in this value of k, we actually have a y-intercept to be negative k. So you would just take your y-intercept value and put a negative on it. So that's what negative k. The experiment is repeated, determine the frequency f that gives a value d of the DCM. So you just find the DCM, but you don't have the DCM. So you will just use your equation. You have your v, you have your f, sorry, you're trying to find your f, you have your d, which is the amplitude, your d is the DCM, and you would have your k. So from that, you just do your equation and you should be getting your answer. And that will be it for this paper. So let's just see how long we have to finish this paper. 1 hour 15 minutes. That's not a lot of time, considering you have to spend a lot of time on your first question as well. So yeah, let's look at the mark scheme and see how we did. So we'll go back to the beginning. So f is the independent variable, okay, and q is the dependent variable. Okay, we did say that, so that's 1 mark. So 1. Keep h constant. Yep, I also did say that. So it's not the density, it's the h. So the thing about Cambridge is, if you think like there's two constants, then Cambridge, they award you based on your correct answers, they don't deduct marks based on your wrong answers. They just ignore your wrong answers. So as long as you state that, you think like, let's say like just now I thought it was the density that has to remain constant, but the height has to remain constant. So I thought it was both of them. So I just write down both of them, and yeah, one of them will be correct. Next one, label diagram of workable experiment, including fan position in line with turbine so that blades of both fan and turbine overlap. Position in line with turbine. Yep, so it just has to be facing directly towards the turbine. So that's one condition. So I think this is 1 mark for all of this, or is it 1 mark for each? I believe it's 1 mark for each. Let's just label it as 1 mark first. So I did label a diagram with the fan in line, okay. Base of fan on same bench as turbine. Yeah. Because there's no way you can have a floating fan. So it just has to be on needs a ground similar to your turbine. Because your turbine is placed on the ground, the bench. So it has to be placed on the bench as well. So that's 1 mark. And fan label and or other label from bench. So you have to label the fan and one other label from bench. So you have Wintermine, cable, pump, pipe, liquid. So I did label all of that. So that's 1 mark. We did all of this, so 1 mark. Label apparatus, showing workable method to collect the liquid from the top of the pipe. Example, hose pipe. Okay, so I didn't do this, but remember towards the end where I was like in the middle of my experiment, I thought it was just water spurting out of the pipe like that, but you would have to draw another pipe connecting the top of the pipe to a collection container. So it is this. I did draw that later on to collect the liquid from top of the pipe. So I did draw this to with the other end over a beaker. Measuring cylinder, at least one label related to collection of liquid. Okay. So that's 1 mark. And then use of stopwatch timer to measure time to collect liquid or to measure time for blades to rotate. So I feel like this, I was thinking of stopwatch, but I feel like that is very human error prone. It's like really inconsistent. Like, because you know how fast like fans rotate? There's no way one person can just look at it and be able to correctly determine the frequency without it slowing down or without any aid. That's why I prompted for a camera, but I don't know if I can include the camera. I hope I can. Maybe I just need to ask my teacher first. Okay. Let's just continue on. I'm guessing I can just give that 1 mark as well. Use of top pan balance to measure mass of liquid leaving the pipe. So yep, I did write that as a balance. So they didn't specify where it must be placed. So yeah, you would normally place it like directly below the collection tube, the collection beaker, but placing it below the initial beaker and calculating the change in mass is also a liable option. Method of analysis, plots a graph of Q against FQ. Okay, we did state that. Against Q, do not accept logarithmic graphs. Yeah, so there's no reason to have a logarithmic graph for this experiment. So let's go to our method of analysis. Plot a graph with F cubed in the x-axis and Q in the y-axis. So it's Q against FQ. So yeah, we got that 1 mark. C is equals to GH times y-intercept. So I did technically get this, but I did not state that C is equals to GH times y-intercept. So I did state that the y-intercept is C over GH. So I don't know if that is 1 mark, but yeah, just keep in mind that when you plot the graph, you don't want to find your y-intercept, you want to find the constants like C and D. Okay, so along with D, I did get that as well. But yeah, I put the gradient is D over GH. So we'll just give 1 mark for that for now, but of course later on, we just want to follow the mark scheme as closely as possible, because as you've seen in 2018, it's pretty much similar, the format of the mark scheme. So next one, additional details including safety considerations. Okay, precaution with reason linked to prevent liquid spilling on bench floor. Okay, so spilled liquid. So I did not state that we need a bucket to prevent spilled liquid. Precaution with reason to prevent air dust particles in eye. That's such a out of, yeah, well, that's really out of like the experiment for dust particles to be in the eye. Aren't dust particles going into our eye like right now? Like, why is it specifically for, oh, is it, I think it's just for, because there's a fan, yeah. Okay. So you have to use goggles. Precaution with reason linked to turbine falling, current turbine to bench. So I did draw that, but I didn't state that, so we don't get a mark for that. No mark. Use ruler to measure h. So we did state that. Place a meter rule parallel to the pipe to measure the height of the pipe. So maybe next time we don't say like measure the height of the pipe, we just say measure h because it's already labeled. So yeah, method to determine mass of liquid. So mass of beaker plus liquid minus mass of empty beaker. Okay, that's one way. Or you can use the mass of container and pipe before minus the mass of container and pipe after. Yep, that's exactly what I did. So now let's go back here. To measure Q, determine the change of mass of the container containing the liquid in time 10 seconds. So I did say change of mass of the container, but I didn't state exactly how to determine the mass of the liquid. So I don't think we get a mark for that. So no mark for that. We have to be specific how we're going to measure the change in mass. Okay, method to determine F, example, measure time T for many rotations. Okay, let's say 10. I did state 10. And period T equals to T over N and F equals to 1 over T. Okay, so for me, I wrote as playback the footage in slow motion to determine the time period of oscillations of the blade. As F is equals to 1 over T, use this formula to calculate the frequency. So I did put as F is equals to 1 over T. Okay, video rotating blades, playback frame by frame, and use timestamp determining period. T is equals to, okay, perfect. So I'm assuming that you can use the video playback as our method of determining as the substitute for the stopwatch. So yeah, mark one of the blades to assist in counting number of rotations. Okay, we did not write this. Method to vary F, example, change of speed, change of fan speed. Okay. Let experiment continue to 10 seconds before changing speed of fan. So changing speed of fan, that gives us the varying F. Wait for steady airflow before starting timing and or collecting liquid. Okay, I did not write that. Q is equals to mass of liquid per unit time. Or method and explanation to reduce uncertainty in Q, use large value of time, so let's say 10 seconds, or mass liquid collected. So divide the total mass by loss by 10 to determine the rate. Okay, that's one mark. Repeat measurements for Q for the same value of F. So for me, I put repeat for different values of F. So that wouldn't be correct. It's same value. So we want to repeat for you want to keep the same value of the independent variable, and your dependent variable would be repeat measurements for the same dependent variable and collect the average. Oh yeah, I was thinking too much of plotting a table. Relationship valid if a straight line is produced. Okay. Do not accept passing through origin. Yeah, because it doesn't have to pass through the origin. Okay, so let's calculate how much marks we got from this. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So 11 marks. That is not good. I thought I got more than 11 marks. 1, 2, 3, 4, 5, 6, 7, 8, 9. Didn't I get 9 marks from this already? 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, I got 9 already. Probably I didn't count a few marks. Yeah, I probably missed out on counting a few marks. 9, no marks here. 10, no marks here. 11, no marks here. 12, no marks here. 13, 14. So 14 out of 15. That's really good. Okay, that's so we just need to keep going like this. Okay, next one. Gradient is v over 4. We did say that. Okay, gradient is v over 4. Y-intercept is negative k. Okay, for 2b, we have 0.667, 0.476, 357, 244, 192, and 132. Okay, 24.7 plus minus 0.2, 17.4 plus minus 0.2, 8.4 plus minus 0.3, 6.6 plus minus 0.4, 4.6 plus minus 0.4. Alright, that's all correct. 6 points plotted correctly, that gives you 1 mark. Yep, just plot the correct points. And error bars, like I said, it has to be less than half a small square. Less accurate to less than half a small square. So yeah, make sure it's accurate relative to the magnitude of your uncertainties for the error bars. Next one. Yeah, it's symmetrical as well. So yeah. Next one to C2, straight line of best fit drawn. Okay, just best fit line. Lines must pass between these values. They have a quota for what lines have to pass through for best fit. That's weird. Or between. Worst acceptable line drawn. Steepest or shallowest part that passes through all the error bars. Okay. Gradient determined with clear substitution of data points into root y. Oh, did I not write it down? I'm pretty sure I did. Oh yeah. Oh, I guess I didn't. Okay, gradient determined with clear substitution of data points into yx. Distance, yeah, this one you would draw the gradient. Gradient determined of worst acceptable line uncertainty is equals to gradient of best fit minus gradient of worst acceptable line. Let's go back to the paper. QP52. To C4, y-intercept determined by substitution of correct points with consistent power of 10. Power of 10 in M. And oh yeah, we have to put the power of 10 in because it's stated that it's 10 to the power of 3. So for our tree first, gradient, clear substitutions of data points into y over x must be greater than half the length of the line drawn. Okay, but what is this? Gradient determined of worst acceptable line uncertainty. We need the uncertainty as well. Jeez. How do you calculate uncertainty of gradient? Gradient determined of worst acceptable. So we take our steepest worst line gradient and shallowest worst line gradient. We minus them, so it's the same way as you would find uncertainty normally, but you would use the gradient half. Yeah, use the gradient as the values. So we have to draw two worst lines. Jeez, that's a lot of gradient to calculate for just 1 mark. gradient determinant of worst acceptable line uncertainty is equals to gradient of line of best fit minus gradient of worst acceptable line. Okay, I guess that's fine. Just calculate the gradient of the best fit and worst acceptable line. Okay, moving on. Y-intercept determined by substitution of correct point with consistent power of tan y equals mx plus c. Y-intercept of worst acceptable line determined by substitution into y equals mx plus c. So that's number 4. We need to calculate the absolute uncertainty as well. So the same way we would calculate the y-intercept by just looking at the graph of your best fit line. Oh no, you wouldn't use the line. You just use y equals mx plus c to calculate your y-intercept. Wait. So I'm guessing in your gradient, you would like cut over here. You would cut in the x-axis. So that's why you would use your equation to find the y-intercept. And y-intercept of worst acceptable line determined by substitution into y equals mx plus c. Yep, you use your same way of your y-intercept of your best fit and your y-intercept of your worst acceptable line. Okay, 2D, v is determined using gradient of v and k. So v is equals to 4 times gradient equals to 4 times what we got just now as the gradient. Yeah. I did say that just now, right? Yeah. Okay, and k is your y-intercept, so k will be equals to negative y-intercept. Yeah. Okay, absolute uncertainties in v and k. So you would use for v is your change in gradient over gradient times v. Or 4 times your uncertainty in gradient. Yeah, okay, that makes sense. And your k is uncertainty in y-intercept. Yeah, it's just your uncertainty in y-intercept since your k is just equals to y-intercept. Yeah. F determined to a minimum of 2 significant figures, so you would use your value of f, and v over 4 is your gradient. So you just use the formula from here, and you make your f the subject, so you would v over 4 times d plus k, substitute your values in, and that should give you f. So yeah. So the thing is, paper 5 is actually really easy, and you just have to really pay attention to what you're writing down. And people often score the highest in their practicals in physics, since physics practicals are actually quite easy compared to like other bio and chem, since there's not much room for error. Its only error is human error. In chem, you could have like chemical errors and all that stuff. Well, I don't take chem, but I'm just guessing. But in physics, it's really not much room for error. And not that you get any errors, but what I mean is like the probability of getting an error is just up to the person. So always check your answers properly, make sure you have the correct units, and yeah, I guess that's it. But I'm gonna do another paper 5, but first I'm gonna go and do something in a bit, so just give me some time. Okay, I'm back. Yeah. Let's move on to the next paper. But for now, I might have to leave soon actually. So again, I have to leave a bit early. Moving on to May June. Oh, sorry, not the mark schemes. Not there yet. Question paper. Okay. Oh, this one. I've actually went through this one like a few times before, but never really like scored well. Let's see how we do now. Why is it? Oh, sorry. 5, 1, 2, 3. My bad. So for this one, you will have to. Probably it's gonna take some time. I have to leave in like 5 minutes, but yeah. So one thing I can say is like, for paper 5, it's literally all the same thing. You always get the same format for everything. Look at it. Draw, make the format, make the procedure, gradient, points, graph, and yeah, about the same thing. But for this, you might have to use this one. It's all the same. So really, paper 5 is like one of the easiest papers. If I don't do well, I'm gonna be so mad. But yeah, it's really easy to do. You might just, I think what really goes to P5 is you just look at the mark scheme. Instead of doing the question papers, look at the mark schemes and see how it is answered. I think doing it is actually a bit of a waste of time. Just look at how it's answered and look at what they want, what Cambridge wants. It's the same in psychology. All of the essay questions, all of the essay papers, look at what Cambridge wants to see from you. You know? Alright, so I actually have to go now, sorry about that. But yeah, thanks for coming into the stream. Hopefully we'll do very well in our A2 papers. And yeah, praying for the best. Nothing like today's paper. Although it wasn't really bad, I thank God for helping me get through the paper. And actually not doing that bad, but it's just below my expectation. But okay, let's try to not think that. I will get good marks, but just don't overthink it, you know? Yeah.